the sound levels? Sound levels okay? Okay, welcome back. We're going to try chalk now. Let's see if we've got the good kind of chalk. And I'm going to start this second lecture with an introduction, again in the spirit of introduction to cosmology. These lectures, I hope, at least at the beginning, will be familiar to most of you, but I'm establishing some notation and ideas that I hope that later speakers will take advantage of. And I'm putting things in an astrophysical context so that as we think about physics, particle physics in the early universe and gravitational physics in the late universe, we have a unifying thread of cosmic dynamics linking them all together. So I'm going to talk about local expansion and gravitational dynamics. Giving the perspectives from Newtonian gravity and special relativity, but I will indicate as I go along why things should carry over to general relativity and where they might not, or where they might vary with other theories of gravity besides general relativity. But before writing down any theories, I'm going to summarize the cosmological principle, which is a kind of variation of Einstein's original assumption of homogeneity, anisotropy, and a static universe, but it is motivated by and well tested by observations in the almost 1 century since Einstein. And the statement is that the universe is nearly spatially homogeneous and isotropic on length scales sufficiently large, and I can take greater than or about 100 megaparsecs as a typical length scale. For example, galaxy number densities varies in space. I said the galaxies are clustered, but if I calculate a root mean square value on a length scale or averaged over a sphere of radius 8 megaparsecs, let me call it about 10 megaparsecs, is about 1. And on much larger scales, those fluctuations are much less than 1. Empirically justifying the assumption of large-scale homogeneity. Now then, to work out cosmic dynamics from this perspective, I'm going to consider a sphere of radius r with the uniform mass density. And I'm going to let the radius r change with time, such that the sphere encloses a constant number of particles. And by particles here, I mean atoms, dark matter particles, photons, etc. I mean stable particles. And these are the particles that dominate the mass contribution. not prescribe how that mass energy changes with time in the sphere, but I will let it change, supposing that I might be describing even relativistic particles here. Although I'm going to set this out as if it were a Newtonian context, the application is much wider. So I have this sphere, a radius r of t, enclosing a mass m of t. The sphere encloses a fixed number of particles. And therefore, I have a mass density, which will be a source for gravity. Rho of t is just the mass divided by the volume. And you will notice here that I am making an assumption. I'm assuming Euclidean geometry for computing volumes. In general relativity, space can be curved. In cosmology, space can be curved over distance scales of hundreds of megaparsecs or much larger. Indeed, it's extremely interesting that observations suggest that space is Euclidean to a high approximation over scales of hundreds of megaparsecs, but it need not be. Certainly over scales of a few megaparsecs, space is Euclidean. There have been searches for deviations from Euclidean geometry and unsuccessfully and on any scales. So now that's the mass density, and now we can require local energy conservation for a test particle whose distance is r of t. And the energy per unit mass of that particle which I will call little e, is the kinetic energy per unit mass, a half of velocity squared. I'm assuming here that the sphere is only expanding in the radial direction, which is appropriate for uniform expansion. And then I have to subtract off the gravitational energy. Great. Now you might say, that's a very peculiar thing. Why should I have such an expression for gravitational energy in general relativity or for relativistic particles? In fact, this is a consequence in GR, general relativity, of the Birkhoff's theorem. Birkhoff's theorem states that any spherically symmetric static spacetime, excluding a sphere, if it's vacuum excluding a sphere, is Schwarzschild. And that is to say, no matter what mass or energy or equation of state you put in for the mass energy contributions in a sphere of radius r, the exterior metric is Schwarzschild. That's general relativity. Now the Schwarzschild metric in the weak field limit, and so here is a weak field assumption that I'm making. I'm actually making two assumptions, weak field and slow motions. Small velocities, and I'll take units such that the speed of light c is 1. That's a special relativistic restriction. And I'm going to assume gm over r is much less than 1 as well. That is a weak gravitational field assumption. So I'm not applying this energy equation in the vicinity of a black hole. I could, of course, write down the corresponding Hamiltonian for a particle moving around a black hole, but that's not necessary. In cosmology, we're typically working far away from black holes, at least I will, in the lectures that I present. So in the weak field limit, the Schwarzschild metric just exactly reproduces Kepler's laws, where this m, in fact, is just a parameter in the Schwarzschild metric. Now, I mentioned that this is a consequence in general relativity because this energy equation will not hold if general relativity is violated. So, for example, if you have fifth forces or if you have additional field interactions, this expression for energy would obviously be modified. This is a minimal theory. And for low velocities, and provided I satisfy this weak field condition, I can get away with a Newtonian treatment. So this is just putting in what M of t is. There we are. That's the energy, and it is conserved for this test particle. So it's independent of time. Okay. What I'd like to do now is to apply this energy equation to different test particles, particles at different radii. I'd like to make different shells. So let's apply two different shells by writing R of t is R0 times A of t, where R0 labels the shell for test particle. And A of t is some kind of universal function of time that describes an overall expansion if A is increasing with time. This is called a uniform expansion. When distances all scale with one single scale factor, that's called a uniform expansion, and it is the only thing that's consistent with the cosmological principle because a non-uniform expansion would lead to inhomogeneities. So with this assumption, then I'm going to ask the question, can I form a quantity that is not only independent of time, but independent of R0, the shell? So I will take my energy equation here, and to get rid of the dependence of R0, which you can see, for example, in R dot, that will have an R0 in it, I will just divide by R squared each side. So E over R squared of t, which is equal, of course, to E divided by R0 squared A squared of t. Well, R dot over R is just A dot over A. And this is minus 4 pi over 3g rho of t. And now you notice that the right-hand side is independent of R0. And therefore, the left-hand side must also be independent of R0. That means that E must be proportional to R0 squared. Or E over R0 squared is a constant, and I choose to call that constant minus 1/2 capital K. And this K is independent of both T and R0. All right. I can rewrite this equation now, and I get Oh, I'm going to make one other definition. I'm going to define A dot over A. I'm going to call that a function h of t, which is called the Hubble parameter. No, for a spatially homogeneous distribution, rho must be independent of R naught. Rho is just the same everywhere in space. But it can depend on time. So think about, by the way, thank you for asking that question. I want to be interrupted with questions. Suppose I have a little volume which is going to grow with time because A of t grows. And I populate this with galaxies. The galaxies will separate. That's the Hubble expansion. But the number of galaxies per volume, well, the number of galaxies per volume doesn't change. And if I have enough galaxies so that this volume is typical of the universe, I'll have an adjacent volume with maybe 3 galaxies in different locations. Now imagine a universe that's filled with galaxies. There's no edge to it. Every volume has about the same amount of mass per unit volume. That's spatial homogeneity. And therefore, the density cannot depend on R0, cannot depend on where I'm located. This is admittedly a strange concept because I am describing a universe that breaks time translation symmetry but retains translation symmetry in space. I'm not constructing a theory here. I'm describing the universe as we see it. We have to ask, why is it that there's an evolution of the universe? Why is it that there is a broken time translation symmetry? That's a fascinating question of early universe physics. But it has no bearing on this. This is merely a statement about the structure of the universe. It seems that our universe looks like a series of snapshots that are spatially homogeneous on the large scale at every moment of time, but whose density is changing by cosmic expansion. That's what we're describing. Are there other questions? Other questions before I continue? This is a very good question. So the only assumption I'm making about dark matter is that I can define an R of T that encloses a fixed amount of atoms and a fixed number of dark matter particles as the sphere changes with time. So I'm assuming that there's no relative motion on average of dark matter particles and atoms. Now, that is not such an observational fact because we cannot see the motion of dark matter. In fact, the only place where people have been able to infer the motion of dark matter is in a cluster of galaxies called the Bullock cluster and several other instances like it, where the technique of gravitational lensing is used to reconstruct the location of the dark matter concentrations and to compare it with the location of the gas, the atoms in these galaxy clusters. In those cases, the dark matter and the gas is observed, in fact, to separate and not to move together. So that's an excellent point. Every principle has a violation. I don't know if that's the general law, but this cosmological principle does. Yes, you could think about the tautology area. So we're making an assumption. There is some empirical weight to it. When we look at most places in the universe, there seems to be a roughly universal ratio of dark mass to atomic mass. It's about 6 to 1. But there are some in the mass ratio. We don't know the mass of the dark matter particle. We don't even know if it is really composed of particles. So I can't tell you what the ratio of number densities is. But barring special circumstances like cluster interactions which separate dark matter from baryons, this is at least a plausible starting point for describing a uniform expansion. That's a really good question. Other questions? Yes? Species. Sure. Sure. You can always write down a local energy conservation law in general relativity, which has a lot wider applicability than this. I'm just doing a toy model, if you like, but one which does amazingly well at describing the universe, and I'll comment on why that is in a moment. Okay, but I wanted to talk a little bit about the Hubble expansion and the Hubble parameter. Parameter is a term here introduced by astronomers. It doesn't have the usual meaning of parameter. This is not one of the 19 parameters of the standard model. And in fact, it changes with time, which you would probably not like for most of the parameters in the standard model. But we're stuck with, astronomers have a terrible penchant for choosing names like dark energy and Hubble parameter. Forgive us. Its present-day value called H naught is 72 plus or minus 3. I think I wrote this on my PowerPoint, kilometers per second per megaparsec. And that occurs at T equals T naught equals 13.7 gigayears. And there are some error bars here, which are something like plus or minus 0.2, but don't quote me on whether it's 0.2 or 0.3. So I want to just rewrite this equation into a very famous form called the Friedmann equation. Because it was deduced by Alexander Friedmann in 1922 from the Einstein field equations. This man was far ahead of his time. He understood the basics of an expanding universe, homogeneous cosmology, and in many respects, he would be properly credited as the father of the Big Bang, although usually Hubble gets that credit, and Hubble really shouldn't because Georges Lemaitre should, for having written a thesis and papers about it in 1927 and even predicting the Hubble expansion before Hubble observed it. But anyway, Friedmann and Lemaitre now get a lot of credit in the field by having key equations and metrics assigned to their names. This is a consequence of general relativity, so it goes far beyond the assumptions which I made here. In particular, it works irrespective of these assumptions. These assumptions really are limitations on R0. Think about it. The velocities squared are proportional to R0 squared. This quantity is also proportional to R0 squared. R0 has dropped out of the equation. Physically, what's happened is we've made a local argument about local dynamics in gravity and extended it to a global cosmological model by assuming that every little patch of space has similar dynamics. That's reasonable given the cosmological principle, but it is more than that. The Friedmann models are a consequence of general relativity for any space-time with a perfect fluid equation of state and with spatial homogeneity. So this is really quite a general conclusion about the Friedmann equation. Now, does it mean that it applies exactly in cosmology? No. There are galaxies. How should I? Let me back up. there are questions of interpretation here. This rho of T, we already saw that the galaxy number density varies a little bit from place to place. So what do we put in for rho of T? Do we put in some kind of local average rho? And what about H? H is not exactly described. Uniform expansion with one value of H doesn't describe the dynamics everywhere. The Andromeda Galaxy is 2 million light years away from us, but it is heading towards us and will collide with the Milky Way in a few billion years. That's not predicted by Hubble expansion. So this is only meant to be a description of the large-scale dynamics in some approximate sense, averaged over scales of hundreds of megaparsecs or more, and it is the job of inhomogeneous cosmology where metric perturbations are introduced to describe how to extend this to say in what sense this is an approximation and to extend the dynamics to a clustered space-time. Let me add that although this derivation assumed that I had something like ordinary matter, the Kepler potential there, you would not expect that to apply, for example, to vacuum energy. But this equation does. It works with the cosmological constant. Einstein's cosmological constant just corresponds to a constant energy density, lambda over 8 pi g. I'm setting c equals to 1 here. And there it is. You can just put in a contribution to rho from vacuum energy, cosmological constant, from different particle species, anything you want. This rho T is the total mass energy density. I gave the numeric value of the Hubble parameter. It has units which are a little strange, velocity divided by distance. There's another way to write those units as 1 over time. And so I'm running out of room here, but at the bottom I'm going to put the value of h naught inverse, the so-called Hubble time. Oh, by the way, I have to do one other thing. When it's 72 plus or minus 3, that historically in astronomy has been written as 100 times h, little h, kilometers per second per megaparsec. And that little h is really the parameter, the fudge factor, which for a good many years was uncertain by 10, 20, 50, even 100%. And only in the last decade or so has become accurate to about 5% or maybe a little bit better. So for many, many years, cosmologists were used to carry along this little h factor because the Hubble parameter, the Hubble constant, its value today, gets used in so many different formulae. So I'm going to, from time to time, carry forward that tradition of using little h in formulae where it matters, and that means you should put in a value of 0.72 or 0.71 according to your preference or whatever else your preference is. When you fit the cosmic microwave background power spectrum, you can measure certain combinations, omega matter h squared, for example, that are more precisely measurable than, let's say, the uncertainty in h naught. That's right. So as a result, cosmologists have introduced a whole host of parameters like little omega, which is omega h squared, and so on. They're all derived. You need a table of conversions to follow the literature on this, and it's unfortunate that one of our basic parameters cannot be measured more accurately than a few percent at this stage. We think our theory is a lot more predictive, though, so that's why the theorists especially like to carry around little h's, because we know that when those astronomers measure it more accurately, our theories are going to be right on. So h naught inverse is an age. It has units of time, and that time is 9.8 little h to the minus 1 billion years. You can put in h equals 0.72, and you'll get something that is remarkably close to our reduced age of the universe. And that's an interesting coincidence, perhaps. And there's also a Hubble length, or distance, and I'll put in the c, the speed of light here, so you just see that I mean something that has units of length, which is 3 h inverse gigaparsecs. So there is a characteristic length scale of the universe of a few gigaparsecs over which, if you look at galaxies separated by that amount, you'd expect them to have relativistic motion. H times r is the speed would be about the speed of light c for this kind of separation. It doesn't mean that the universe is constrained to be smaller than 3 h inverse gigaparsecs, which is about the 4 gigaparsecs I mentioned in my last talk. The universe could be infinitely large, for all we know. But it does mean that you cannot apply Newtonian non-relativistic dynamics on the scales of gigaparsecs. You have to use the full general relativity or another relativistic theory. Okay, can I lower the board and cover this up? I'm going to next introduce the density parameters omega. Since we've already referred to them a little bit, I'll just give the definitions of them. Talk about omega for the different species that we know exist in the universe today. And then we'll talk about the solution of the Friedmann equation. Small eraser makes it a little laborious to cover them. Okay. I guess I can use this also. Now, for the density parameter, I am going to follow the usual conventions that it's not changing with time. Subscript 0 here means present-day values averaged over a large enough sphere to get a fair sample of the universe, several hundred megaparsecs or so. And so this omega is referencing the present density and the present Hubble expansion. And this is often with a distinction for different species. If I describe a species by labeling it X, so this X, this could be photons, it could be neutrinos, it could be atoms, which are usually called B for baryons, B for atoms. Then I will have an omega sub X. Which uses the density of that species, the average density of that species today. And today, M is the total matter in quotation marks, which means atoms plus dark matter. So omega matter is about 0.27. Omega, I will write it as dE for dark energy, is about 0.73. Omega of baryon or atoms is about 0.044. I'm not putting the error bars, and a lot of the uncertainties come from the value of little h. So, but you can find those in various places, and in my write-up for the notes, I will give the latest estimates of this. Using the density parameters and the Friedman and the Hubble parameter, you can rewrite the Friedman equation in a couple of useful ways. This omega sub k takes this energy constant of Newtonian physics, which in general relativity we'll find reflects curvature of space, and treats it as if it were a contribution to density solely for the purpose of saying that all the omegas have to add up to 1. And you can see from the numbers given that omega sub k is small. A bound on its absolute value is about 0.02. Well, that's extremely interesting for many reasons, but I will say more about it later when I talk about inflation. Okay, I want to talk next about a graphical solution of the Friedman equation. You can learn a lot by knowing how to look at your equations. Solving it by heart. I'm going to write the Friedman equation in this form. By something that looks very strange, but you'll have to bear with me. Remember, rho is a function of time, but A is also a function of time, and so perhaps rho can be written as a function of A. We will see that it generally can. So why would I want to write the equation this way? Because you can compare it with the following. One half x dot squared plus phi of x is equal to E. This is the equation of energy conservation for a particle. And you know, for example, how useful this can be even if you're not restricted to one Cartesian coordinate. For example, the Kepler problem. Part of its solution involves using angular momentum conservation to take the energy conservation in 3 dimensions and write the tangential velocities, tangential kinetic energy, using angular momentum, and then getting an effective potential, which combines the Kepler potential, the gravitational potential, together with an angular momentum piece into an effective potential. So this equation for the Friedman dynamics has exactly the same form as that of an effective particle in an effective potential in Newtonian mechanics. And you know how to solve these. You make a graph of the effective potential and look at lines of constant energy, look at the existence of turning points and at the initial conditions. So I'm going to make a graph here of this phi of A for 2 common cases. One is non-relativistic matter, where rho is proportional to 1 over A cubed of T. Why is that? Well, it's because I remember the sphere that I started out with, it enclosed a fixed number of atoms. These atoms are non-relativistic, so their mass energy density is just the rest mass. That total rest mass is constant. I chose my sphere to enclose a constant rest mass of non-relativistic matter. So rho just goes down with 1 over the volume. Physical volume goes as A cubed of T. So let's look at this. That says that V of A is proportional to minus 1 over A. Well, that ought to look very familiar from Newtonian mechanics. This is just the Kepler potential without an angular momentum barrier. It's a Kepler potential for radial orbits. And no surprise there, our cosmological model has radial motions, not tangential motions on these large scales. So you know what the solution of this is graphically. See if I can get some colored chalk here. Well, let's look at our energy constant. It looks like E is taken by minus K over 2. Well, I think that's familiar. I defined it that way before. So if K is non-zero, I can have different possibilities. This would be K less than 0 or K greater than 0. Remember, what this energy equation tells you is that your trajectories have to lie below the energy level. So models with positive spatial curvature, with this constant K greater than 0, in a matter-dominated universe, expand to a maximum A of t, then turn around. This is a turning point. Whereas, in a non-relativistic matter-dominated universe, open models, or spatially flat models, K equals 0 along the axis, there the energy line is always above the potential, although it asymptotes together for the zero curvature case. And so there is no turning point. Those models expand forever. So this is the simple Friedmann dynamics, which has been known now for 90 years since Alexander Friedmann first wrote it down. It's easy to see at a glance. So what we call a matter-dominated universe expand always, given that they start out expanding, if K is less than or equal to 0, and they halt and collapse if K is greater than 0. Let's look at another case. This is going to be quite different. This is called de Sitter space, or de Sitter space-time. It's a space-time that's dominated by a cosmological constant. So here rho is a constant, and now V of A is proportional to minus A squared. It is an inverted harmonic oscillator. Of course, the motion is not harmonic motion. You can again draw the different curvature lines. Actually, for the de Sitter space, this de Sitter space is quite interesting because there are many different coordinate systems that one can use, and some of them have spatial curvature and others do not. But in the usual Robertson-Walker metric, the de Sitter space is K equals 0. And those spaces will then start out with a very small a and expand, but the fact that the separation between the energy level and the potential is growing with time means that A dot grows with time. In fact, it's very easy to show A grows exponentially in time for these models, and they have a constant bubble parameter. But there are other variations you can have. You can have a cosmological constant with universes that are spatially closed or open. The open universes will not have a Big Bang. So you often will see in these parameter plots of matter versus dark energy, there's a little corner which says no Big Bang. That's these models. These models have no Big Bang present in them. Okay, and finally, the lambda CDM model, as its name suggests, combines these two, at least for most of the history of the universe. And so we have something that looks like that. When I say matter or lambda dominated, I mean that the primary contribution to rho of T is given by, in this instance, non-relativistic matter, whose density goes like a to the minus 3. And then at late times, this has diluted away. The matter has diluted so much, a to the minus 3 has grown so small that the constant lambda density, vacuum energy density, is predominant. And now you can see, well, very interesting dynamics. You can have different kinds of universes here, including some without a Big Bang, depending on where you are on this graph. Of course, the zero curvature case, and then the open universes. Again, observations suggest that we live in a universe very close to the k equals 0 line. And hence you can see that in such models, the expansion will decelerate until you pass the maximum. Why do I say decelerate? A dot squared, the kinetic energy, is the difference between the energy level and the V of A. As you evolve to the right, that shrinks until you reach the maximum. And that means that A dot was decreasing. That's what we mean by a decelerating expansion. But once you're past the maximum of that effective potential, then A dot grows with time. That's acceleration. Yes? No. No. Currently we are somewhere around here. And there will be an interesting little homework exercise to calculate at what value of A does this maximum arise. But I want to say something more about this maximum. In 1917, Einstein constructed the first cosmological model using general relativity, his newly found theory. And not knowing any better, he assumed not only was the universe homogeneous and isotropic on the large, but that it was also static. There was no obvious motion in the heavens that perturbed Einstein. Remember, in 1917, the nature of galaxies was not even known. Hubble only revealed that the little spiral nebulae in space that had been studied by astronomers, that they were entire island universes, as they were called at the time. He only discovered that in the early to mid-1920s, mid-1920s. So Einstein had very little basis for speculation, except his own intuition, which was obviously very good, but not in this case. This is the model he picked. This is the Einstein static universe. Now, if you were refereeing Einstein's paper in 1917, what observation would you make to him to call into question his model? Stability. His model is obviously unstable. That was shown a few years later. I forget if it was by Milne or by Eddington. but it becomes really easy to see once you follow this Newtonian-like description of cosmology, which is fully compatible with the Friedmann equations. So this tells you graphically by eye the character of dynamics. It does not tell you the solution A of T. For that, you have to turn usually to a numerical solution, a computer solution, although for a number of simple cases of rho of A, the solution is analytic, and I will summarize those for you. Before I do, let me ask if there are any questions on this. The CMB is not quite enough to determine all these parameters really well. You have to combine CMB and large-scale structure. One way to remind you about that is, remember this parameter space plot, which I said it was mass density and acceleration or dark energy, but now I'm going to say what it really was. There's this, I put 1 here, 0, 1. This line is k equals 0. So if matter and cosmological constant are the predominant constituents, then when they add up to 1, that means there's no curvature. And if you look at the contours of the CMB constraints look kind of like this. So you have to find some other constraints, and these different CMB models have the Hubble parameter changing along this sequence, because really what the CMB can fit well is omega matter h squared. So if you can set the Hubble parameter and then use the CMB, then you get a much better measurement. And there's been a lot of debate in the literature among the observational cosmologists about how the different fits are done. Is it really fair to hold one parameter fixed and vary the others? I think my view at a distance is that the parameters, the multi-parameter fits from different surveys are a very good way to proceed, and they lead to not only good estimates with error bars, but to consistency checks. The fact that there were several other ellipses in this diagram that intersected the same place are consistency checks. This is perhaps the cleanest one. The CMB constraints are probably the least subject to astrophysical complexities. Things that deal with clusters of galaxies or things that deal with Big Bang nucleosynthesis. I mean, there are different astrophysical complications that can arise, so you want to use a variety of techniques. But you need the Hubble parameter. You somehow need to fix the Hubble parameter to make this go. CMB data alone cannot determine the Hubble parameter. Are there other questions? Okay. Actually, before I talk about the solution, I want to say how the scale factor is related to cosmological redshift, the observational redshift. So let me take a few minutes to do that. I'm going to draw a space-time diagram over a local region of the space, small enough so that I can, again, use the same ideas of, in this case, special relativity. I do need special relativity. So I'm going to measure distance from some place and time. This is the world line of some observer. Let's say some galaxy. And I'll suppose that all the galaxies that I'm putting down here participate in this uniform expansion. They're what we call co-moving observers. So co-moving observers have separations that exactly obey Hubble's law. And they're idealizations, but we can correct by using local Lorentz transformations to boost the frames of co-moving observers when we need to. And I'm going to put some time of emission of light from a neighboring galaxy that has a different world line. And this galaxy, you'll notice, is moving away from the first one. As time increases, the separation grows. So this I'm going to call an emitting object, an emitter. And it's also a co-moving observer. And I'm going to send a photon from the emitter to the observer at a 45-degree line. I'm going to assume that the separation at the time of emission is d little r, and the separation in measurement is dt. And this is done over a small enough region of space so that special relativity holds. There's no space-time curvature effects. Even in general relativity, space-time is locally flat. You can always apply special relativity if you're far away from any space-time singularities, and I'm just out here in interstellar space where this is perfectly viable. So dt is dr. That's the light cone condition. And dr, I'm going to write as dr0 times a of t sub e. Why is that? Remember, r is r0, this so-called co-moving distance, which is fixed for each observer. Here I'm going to take this one to be, if you like, at r equals 0, this one to be at r0 times a. And a of t is universal for all pairs of galaxies. So the separation grows with a of t. The physical separation at time t sub e is a of t sub e times dr0. So that's the separation which the light has to travel. Okay, so now I'm going to work in the emitter's rest frame and look at the photon form momentum p mu, and this is all special relativity. So I'm taking local Lorentz frame, special relativity. I use an underscore to denote the spatial components, the three momentum, and I group together p superscript 0, which I call E, the energy, and the spatial components like this. That's my notation for grouping together space and time components. And I want to label this photon by the energy it had when it was emitted. So I'm going to call that E subscript little e for emitted. And I'm going to factor that out from both the energy and the momentum. And for a photon, the momentum magnitude equals the energy. I'm going to put in a -1 for motion to the left. I'll take my spatial coordinates to be increasing to the right. Photon has to move to the left. So that's the form momentum of the emitted photon. Its form momentum is conserved in a local Lorentz frame. And I'm going to now get the measured form momentum by dotting it into the forward velocity of the observer. And that forward velocity, again, special relativity, setting c equals to 1. V is the velocity of the observer relative to the emitter. The emitter is moving to the right as viewed by the observer. That means in the emitter's rest frame, the observer is moving to the left with the same velocity, and that velocity is small. How big is that velocity? V sub r is h at t sub e times dr, and dr is differential. It's going to be very small, so dr is very small. I can therefore neglect the v squared in the denominator and write this as 1 and h of te times dr. So now I get the energy as measured by the co-moving observer on the left. I just use the observer's fore velocity projected into the fore momentum, and in doing so, I'm using the typical astrophysicists or relativists convention on the Lorentz metric. Oh, my apologies to all the particle physicists here. You could change the signs in your notes. All right, so that leads to an energy change And by the way, both of these observers are co-moving. The first one was co-moving. The energy was E sub E. The second one was also co-moving. The energy is less. So the energy measured by co-moving observers changes with time, and it changes according to dE over E is minus the velocity. That's just I did a lot of work to get the special relativistic Doppler formula in a non-relativistic limit, but I did this because I wanted to emphasize the role of co-moving observers and the fact that you don't have to abandon special relativity just because you're doing cosmology. And I'm going to show you in a moment that you can even apply the lessons of special relativity clear across the universe. Okay, but dr is dt. And h is what? A dot over A. So I have an A dot dt over A. dE over E is minus dA over A. That is, as the universe expands so that A increases, the energy of a photon as it passes each co-moving observer decreases, such that E times A is constant. And that is true not only for a pair of infinitesimally close co-moving observers, it's true everywhere along the world line. Just a moment. Sorry, I can't raise that. Differentially, when the universe expands by, let's say, 1%, the energy as measured by a co-moving observer decreases by 1%. Now what I'm saying is that although I made this argument locally for one co-moving observer and the next one, I can keep doing it. I can apply it to the next one and the next one. And pretty soon I'm clear across the universe. The power of special relativity extends all the way across the universe. That's really cool. I'm going to have to cover this up in the last few minutes, so bear with me. So, what have we found? We found that the energy redshifts, I'm going to write energy in terms of photon wavelength. I can't write Planck's constant as little h, because I've already used little h for Hubble, dimensionless Hubble parameter. And you might not like seeing h bars, but I'm an astrophysicist. I'm kind of used to carrying along the h bars for a little while. So here we are. This is just the energy frequency or energy wavelength relationship for photons. And if this is proportional to A of t, it implies that lambda emitted divided by lambda observed is A of t observed over A of t emitted. The wavelengths stretch. The observed wavelengths, and this will always be less than 1 for an expanding universe. So the wavelengths of light, as measured by co-moving observers, grow, and it's conventional to define A of T naught equals 1, where T naught is the present day. And by present day, I don't mean June 2nd, June 3rd, 4th. Anything within about a million years is plenty good enough for astrophysical accuracy. And to write let me see that I have this the wrong way around. It should be A of lambda emitted should be less than lambda observed. What am I doing? I have this backwards, sorry. If you're puzzling over an equation, then there's a good chance that I have made a mistake, so please correct me. And so, the previous equation was also right. Well, E should go as 1 over A. That's why, thank you, that's why I made a mistake. So then lambda goes as A, so this should be, it'll be less than 1 A of T. Do I have it right now? So lambda observed is greater than lambda emitted by a factor 1 plus z. Z sub e is called the redshift, and this equation here is called the redshift time relation. So when you read in the newspapers about the discovery of the most distant galaxy or quasar, they will always tell you that the light emitted from that galaxy was emitted, let's say, 100 million years or a billion years after the Big Bang, or that it was emitted 13 point something billion years ago. That's not what the astronomers measure. They actually measure the redshift. So when I read those articles, I always want to know, what is the redshift? I could care less about how you converted redshift to cosmic time, but the newspapers want it. So in order to make that conversion, you have to know the function A of t. To know A of t, you have to know the cosmic composition and expansion history quite accurately. It's not what astronomers recommend. Okay, I think it's time for me to stop. So my next lecture will pick up with the solutions of the Friedmann equation for different fluid components of the universe, and then we'll start into